All right. Hi, everyone. I hope you're having a good day. So this is the recorded lecture for class on Monday, October 17th. And we're going to talk a little bit more about subspaces. So let me say quickly, what are the goals for today? So number one is to give some more examples of subspaces. Don't worry, I'll recall the definition. Give some more examples of subspaces. And then number two is to discuss the concept of basis of a subspace. Okay, so just discuss the concept of basis of a subspace, and there's going to be several things, several other like mini concepts that are related to what a basis is. Okay, so I'm going to start by just recalling what the definition of a subspace is that a subset H in Rn is called a subspace if, well, three properties need to hold. So the first property is that the zero vector has to be in H. So this is a subspace. The second property is that if you have two vectors in H, then their sum, u plus v, has to be in H as well. This is sometimes called closed under addition. And the third property is that if u is in H and c is a scalar, so it's a real number in R, then cu is also in H. So this is called closed under scalar multiplication. Apologies for the small writing that says closed under scalar multiplication there. Okay, and so we saw a whole bunch of examples last class, which was already 2 weeks ago. We saw a whole bunch of examples last class for this concept. And at the very end of class, we gave two particular examples that I want to spend a little bit more time talking about today. So the examples are, let's let A be an m by n matrix, right? So then we had these two spaces, which we called the column space of A, which was equal to the span of the columns of A. And then we had something called the null space of A, null of A, which is the set of solutions to AX equals the zero vector. Okay? And what we showed last time is that these are both subspaces. Okay, that for any matrix A, its column space and its null space are both subspaces. Okay? Okay, so this is the span of the columns of A. And by the way, I should also say, just this is also another way of stating this is the set of all B in Rm such that AX equals B has a solution. Okay, this is just another equivalent way of stating what the column space is. Okay, so the definition in blue and the definition in red are the same thing. Okay, so let's look at an example just to try to compute these things, right? So so maybe I should just recall also that if I take any vectors v1, vp in Rn, then the span of all of those vectors, so the span of v1 up through vp, is a subspace of Rn. Okay, so this was a result that we proved last time, and then all of these other examples of subspaces that we had, like all of Rn and a plane through the origin in R3 and a line through the origin in R2, If you go back to your lecture notes on October 3rd, there's all of these different examples. They could all basically be written in this form. They're all the span of a certain number of vectors in Rn. That automatically gives you a subspace. Okay, so what I want to do is do an actual example where A is a particular matrix, and we're going to go compute this column space, and we're going to compute this null space. Okay, just to show like specific examples of these subspaces. Okay, and in general, not only is this an example of a subspace, this span of V1 through VP, but it's often a good way to specify a subspace. So if you're talking about a subspace and somebody's asking you what subspace, usually a good way to specify that subspace is to say, oh, it's the span of these vectors. Okay, it's a good way to name your subspace, to tell people what you're talking about. Okay, so let's look at a particular example with a particular matrix. Okay, so I'm going to let A be the following matrix. It's going to be a 3x5 matrix. I think I took this right from the book or maybe from an earlier edition. So -3, 6, -1, 1, -1, and then 1, -2, 2, 3, and -1, and then lastly 2, -4, 5, 8, and -4. Okay, so this is going to be the matrix A. And then I'm just going to tell you what the row-reduced echelon form of A is. I don't want to do it all. We know how to row reduce. So the row-reduced echelon form turns out to be this: 1, -2, 0, -1, 3, 0, 0, 1, 2, -2, and 0, 0, 0, 0, 0. Okay. So this is what we have to work with. We have a matrix A. This is a 4 here. And then we can write down its row-reduced echelon form. You just have to do a standard row reduction. And so now we want to talk about, how do we say what is the column space of A and what is the null space of A? Okay, well, the column space of A is easy, right? The column space of A is just the span of the columns. Right, so we can write the column space of A, i.e., so that is, the column space of A is just the span of all of these columns. So -3, 1, 2, I'll say columns of A. So -3, 1, 2, 6, -2, -4, -1, 2, 5, 1, 3, 8, and -1, -1, 4. Okay, this is the span of A. Let me use curly. It's the span of this set. Let me use curly braces. So span of this set. So this is the column space of A. You just write down all the columns of A, and their span is the column space. And important note here, that we use A, not the row-reduced echelon form of A. Okay. Okay, so this is the span of the columns of A, right? This is the column space of A. It's the span of the columns of A. Okay, you just write down the columns, and that's what it is. So the null space of A requires a little bit more work. Well, the null space of A, what we're trying to do is we're trying to figure out all of the solutions to AX equals 0. So what we're going to do is we're going to solve AX equals 0, and we're going to write it. We're going to write the solutions in parametric form. Okay, so that's the idea. We're going to solve AX equals 0, and we're going to write the solutions in parametric form. So this is where we're going to use row-reduced echelon form of A, right? I mean, we know what the row-reduced echelon form of A is. We wrote it down. Okay, so the augmented matrix. So the augmented matrix in row-reduced echelon form is what? It's just this matrix 1, 2, 0, -1, 3, 0, 0, 1, 2, -2, 0, 0, 0, 0, 0. And then since we're solving AX equals 0, this last column is just all a bunch of zeros, right? And no matter what row operations you do on it, everything stays a 0. Okay, and so what does this translate to in terms of equations? Well, remember, so we have our pivots, right? Our pivots are here in the first column and in the third column. So we write the pivot variables in terms of the non-pivot variables, right? So this tells us we have what? x1 minus 2x2 minus x4 plus 3x5 equals 0. And then we have x3 plus 2x4 minus 2x5 equals 0, and then just 0 equals 0. And so if we solve for the pivots in terms of the non-pivots, that gives us that x1 is equal to 2x2 plus x4 minus 3x5. And likewise, x3 is equal to minus 2x4 plus 2x5, right? We're just isolating x1 and x3 over here. And so remember, so how do we do this with parametric form? This just says that our solution space is given by any vector of the form, well, 2x2 plus x4 minus 3x5. That's our x1. Then x2 is a free variable. x3 is given by this expression, minus 2x4 plus 2x5. x4 is a free variable, and x5 is a free variable. So the solution space is just given by any vector in this form is going to be a solution where you can choose any values you want for x2, x3, and x4. And another way to see this, right, if we write this in parametric form, is that we can write it as x2 times something plus x4 times something plus x5 times something. How do we figure out the entries? We just look for the coefficient of x2 in all of these vectors. So it's going to be x2 times 2, 1, 0, 0, 0, right? Those are the coefficients of x2 here. We have a 2, a 1, and then all zeros. Then x4 is going to get 1, 0, minus 2, 1, 0, right? Because you got x4 here, you get nothing here, then a minus 2 here, and a 1 here, and nothing here. And lastly, x5 is going to be minus 3, 0, 2, 0, 1. Okay. So this is how we write our solution space in parametric form. But what is that saying? If we're saying that we want everything that's a linear combination of these three vectors with any possible coefficients, right? Remember, this x2, x4, and x5 are completely free variables. They can take on any values at all. Well, that means that the set of everything that can be written this way, in other words, we're just saying the solutions consist of all of the linear combinations of this vector, and this vector. So I'm going to write it on the next page. So what we conclude is page 3. So we conclude that the null space of A, is equal to the span of, well, exactly these three vectors over here. This one, and this one. Right, so it's the span of 2, 1, 0, 0, 0, and 1, 0, minus 2, 1, 0, and minus 3, 0, 2, 0, 1. Okay, so this is how we can write the column space of this matrix. The null space of this matrix. Right, so we have these two formulas. So this is the column space of the matrix. You just write the columns down, and it's just the span of all those columns. And then this is the null space of the matrix. In the null space, you actually have to do a little bit more work. You actually have to solve the equation AX equals 0 and write your solution in parametric form. And when you write your solution in parametric form, it's always going to be some variable times some vector plus some other variable times some other vector, and so on and so forth. And what you need to take for the null space is just writing out the span. It is just the span of all of these vectors that you get when you write the parametric form. Okay, so this is how we do it. And so in this case, we get that the null space is equal to this span of all of these vectors. Okay. So, and this works for any matrix, right? And maybe, by the way, let me just remark, right? If A is m by n, then column space of A is a subspace. Where does it live? It lives inside each of these vectors in the column space has length the number of rows, right? So it lives inside Rm. So the column space lives inside Rm, and the null space of A, remember this null space of A, we're looking at solutions to Ax equals 0. So if A is m by n, then the x's are vectors in Rn, right? So in this case, the null space of A is always going to be a subspace of Rn. Okay, so column space is lies inside Rm, and the null space lies inside Rn. Okay, great. Okay, so we wrote these, in a pretty good way. I mean, so at least for the null space, it really seems like we need all three of these vectors, right? I mean, when we're writing down the solution space, we use all of these vectors to get the solutions. We kind of need all three of these free parameters. Whereas for the column space, maybe we don't. Maybe we're saying it's the span of all of these columns, but maybe we don't really need all of them, right? I mean, in particular, it's pretty easy to see that we don't need both of these vectors, right? Because the second vector here is just twice the first vector, right? So if I got rid of this second vector, if I got rid of 6 minus 2 minus 4, the span of what's left would still be the same, right? Because throwing in 6 minus 2 and minus 4 doesn't add anything to the span, because I already have 6 minus 2 minus 4 from minus 3, 1, 2, right? I can already multiply this by 2. That's going to give me this vector. So anything I can write as a linear combination of all 5 of these vectors, I could write it without using the 6 minus 2 minus 4 term, right? If I had like one of these and one of these, I could just rewrite it as, minus 1 of these, because it's one of these, and then this one of these is the same as minus 2 of these, right? So I would have just, instead of 1 and 1, I could have 1 and minus 2, which means I just have a minus 1 here. Okay, and I could rewrite it without ever using this. Okay, so this idea leads to the idea of a basis of a vector space. So let me give a definition here. So definition, if H is a subspace of Rn, and now this can be any n, then a basis of H is any linearly independent set in H whose span is all of H. Okay, so it has two parts. It needs to be linearly independent inside H, and the span of it also needs to be all of H. So for instance, if H is a subspace, you usually present it by saying, well, it's the span of these vectors. And so do those vectors form a basis? Well, it's certainly true that if H is the span of a bunch of vectors, then their span is H. But what you need to do is also check that they're linearly independent. So you can think of having a basis, having it both linearly independent and a span is like, it's kind of the most efficient way to present a subspace. Okay, so over here, for instance, I can say that the column space of A is the span of all of these different columns. But what we saw is that I don't really need 6 minus 2 minus 4. It's kind of a waste. I don't need it. So, and in particular, the set is not linearly independent, right? Because, 2 of this plus 1 of this plus 0 of all the other stuff is equal to 0. So if I wanted to present this using a basis, I certainly couldn't include both of these vectors. I'd need to take out one of them to have any chance of being linearly independent. And what we do in order to try to have a basis is if we have a bunch of vectors that span the space, we take out kind of all the redundant ones until what we're left with at the end doesn't have any redundancies, and that's going to mean that they're linearly independent. Okay, so that's maybe a little bit highfalutin, and it's not clear exactly what's going on. So we'll show some examples that tell you what's actually going on. But for now, we have this definition that if I have a subspace, a basis of H is a linearly independent set that also spans. We should think of these two conditions as kind of like, this is a kind of like bigness condition, right? These vectors have to span H. There have to be enough of them to get all of H in the span. And this linearly independent is a kind of smallness condition, meaning the vectors have to be linearly independent. You can't have so many of them that you start to have that some of the vectors are linear combinations of the other, right? That would be a linear dependence. You can't have so many vectors that you start getting linear dependencies, right? That's no good. Okay. So let's just do a couple of examples to start with. So one example, we could take H to just be all of Rn itself, right? Remember, we showed in class last time that Rn is a subspace of itself. So then the following set is a basis. The set E1, E2, up through En is a basis, right? Remember, E1 is 1, 0, 0, 0, 0, 0. E2 is 0, 1, 0, 0, 0, 0, 0, and so on. So if I let H be Rn, then this set is a basis, right? Because we've seen already before that they are linearly independent. And they span Rn. Okay, so we've seen both of these things before. And notice what we called this before, right? We called this the standard basis, right? We called these the standard basis vectors. So beforehand, this was just a title, but now you see why I gave it this title, right? They're the standard basis vectors because they form a basis of Rn. They're linearly independent. There's no way to take a linear combination of these guys and get 0 unless you're going to use 0 for every coefficient. And they certainly span Rn. If I have any vector Rn, I can decompose it into its first coordinate times E1 plus its second coordinate times E2 ... plus its nth coordinate times En. Okay, so this, as an example, is definitely a basis. So maybe I'll just give one more example here. I'll say, in fact, not in face. In fact, if A is an n by n invertible matrix, so I take any n by n invertible matrix. So in particular, I could take the identity, right? The identity matrix is invertible, right? Because its inverse is just itself. The identity times the identity equals the identity. And in fact, we know that if A is an n by n invertible matrix, then the columns of A form a basis of Rn. If it's an invertible matrix, then the columns of A form a basis of Rn. And the reason is that their linear independence and spanning Rn both follow from the invertible matrix theorem. It's the invertible matrix theorem in section 2.3. Right, remember the invertible matrix theorem was this theorem that had like 12 different independent criteria for a matrix to be invertible. One of them was that the columns span Rn, and another one of them was that the columns are linearly independent. So if you have an invertible matrix, the columns span Rn and the columns are linearly independent, and that means that the columns have to form a basis, because that's all you need, that they form a basis of Rn, because they span Rn and they're linearly independent in Rn. Okay. And what we should notice is that the first, let's call this maybe example 1, and this is going to be example 2. In fact, example 1 is just example 2 with A equals the identity matrix, which is certainly invertible. Right? If I do this example, if I take the identity matrix, then its columns are exactly these standard basis vectors, right? 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, and so on. Okay, so these are a couple of examples of subspaces of Rn, and in this case, both times the subspace is just Rn itself and a basis. Okay, good. Okay, so how do you actually find bases? How do we compute these? So how do we compute a basis? Well, in general, there's maybe not one algorithm to do it, but let's look at a very specific example. Specifically, if A is a matrix, how do we compute a basis of the column space of A and the null space of A? How do we compute bases of these two spaces? Right, we know they're both subspaces, and we figured out a way to kind of write them down, but we didn't necessarily have a basis. Okay. So let's start first with the null space, actually. Null space of A. And the answer is that we do exactly what we did before. And we automatically get a basis. Okay, we do exactly what we did before, and we automatically get a basis. All right, so let me show you why that's true. So let's just look back at this example, right? We had this matrix A. Let's say you want to compute a basis for the null space of A. Well, you compute its row-reduced echelon form, you solve the equation AX equals 0, you write it in parametric form, and you get x2 times this vector plus x4 times this vector plus x5 times this vector. And then we wrote the null space of A as the span of those three vectors. So we know these three vectors span the null space of A. I want to claim that we know they're just always going to be a basis also. And well, the reason they're going to be a basis is because, well, what do we have to check? We have to check that they're also linearly independent. Okay, so why do we know these things are linearly independent? Well, I'm not going to write a formal proof. I'm just going to try to convince you guys in this case, and then the the general case is the same. Okay, so why are these vectors linearly independent? Well, I'm going to rewrite them on this page. Okay, so why? Well, at least in our example, what are our vectors? It's 2, 1, 0, 0, 0. And the next one was what? 1, 0, minus 2, 1, 0. And the last one was minus 3, 0, 2, 0, 1. Okay, so why are these linearly independent? Why should these be linearly independent? Well, the point is let's suppose that we have something like A times 2, 1, 0, 0, 0 plus B times 1, 0, minus 2, 1, 0 plus C times minus 3, 0, 2, 0, 1. Let's suppose that we have some linear combination here that's equal to the 0 vector. And you know what? I'm going to rewrite this. I'm going to rewrite this a little bit neater because showing it graphically is going to be a good way to make this work. So let's say that I'm just going to rewrite the vectors. This is 2, 1, 0, 0, 0. This next one is, oh, wait, let me, let's say, so suppose that we have A times this plus B times 1, 0, minus 2, 1, 0, plus C times minus 3, 0, 2, 0, 1. Suppose that this is equal to the 0 vector. Well, let's look at the second position in these vectors. If we're going to add up A times this vector plus B times this vector plus C times this vector and get the 0 vector, well, the second component certainly needs to be 0. And that means the coefficient over here is definitely going to have to be 0. Okay, so from the red circle, we're going to get that A equals 0, I'll say from the red loop. Now let's do the same thing, but in a different color in the fourth position, right? In the fourth position here, I have 0, 1, 0. So if I'm going to take something from this vector, something times this vector, plus something times this vector, plus something times this vector, and get the 0 vector, then it better have a 0 in the fourth position. And that means, well, these two don't contribute. That means whatever my coefficient of this vector is had better also be 0. So that's going to tell us that B is equal to 0. So I'm going to need to have B equals 0 from the green loop. And then lastly, let me use purple. If I look at the fifth position, well, same idea. If I have A times this vector plus B times this vector plus C times this vector equals 0, then it needs to be 0 in the fifth position, which means that I need to have this coefficient be 0. And so that's going to tell me that C is equal to 0. This is from the purple loop. And so all in all, well, we said that if we have a linear combination, then we just showed that all of the coefficients have to be 0. So what this means, we conclude that the three vectors are linearly independent and thus form a basis. Okay. All right, so in fact, we get these vectors just from solving. Well, we know that they span, but it turns out they're also always going to be linearly independent, and they're always going to form a basis. And in fact, this idea of the proof will always work as long as you draw your loops at the positions that correspond to the free variables, right? So in this example, our free variables corresponded to x2, x4, and x5. Well, when we're doing what we're doing over here, if you draw this in the second position, the fourth position, and the fifth position, because that's x2, x4, x5, then everything here is always going to work. Okay, but we can accept this as a fact. In order to calculate a basis for the null space, you just write down the solution, the system AX equals 0, you solve it, and you write it in parametric form, and what you get is going to be a basis. Okay, so that's how we get a basis of the null space. Okay, so what about a basis of the column space? That is going to be a little bit more involved. So I'm going to start a new page for that. So here, so this is page 5. So how do we find a basis? So we did the null space of A. Now we're going to do the column space of A. So let me say the column space of A. Okay. Well, first, let's look at an idea. Well, I want to recall what the row-reduced echelon form of A is. Row-reduced echelon form of A is, it's given by this matrix over here. I'm just going to copy it down onto this other page. So the row-reduced echelon form of A, if we recall, is equal to 1 minus 2, 0 minus 1, 3, 0, 0, 1, 2 minus 2, 0, 0, 0, 0, 0. Okay? And if I wanted to take the column space of the row-reduced echelon form of A, well, this is equal by definition. It's the span of 1, 0, 0, minus 2, 0, 0, 0, 1, 0, minus 1, 2, 0, and 3 minus 2, 0. And it's not hard to see that 1, 0, 0, and 0, 1, 0 form a basis. So just these two vectors here, right? That these two form a basis. Just marking them in red, form a basis of column space of the row-reduced echelon form of A. Why? Well, they're clearly linearly independent. Right, I mean, 1, 0, 0, and 0, 1, 0 are certainly linearly independent vectors. They're standard basis vectors. And they also span this, because this column space, if you notice, every vector here has a 0, right? And so if you're in this span, if you're any linear combination of these things, your third component is going to be a 0, no matter what. So they span column space of the row-reduced echelon form of A because this column space of row-reduced echelon form of A is just equal to, all vectors in R3 with a 0 in the last entry, right? And so if you want all vectors in R3 with a 0 in the last entry, it's certainly true that if I take these two vectors, I can get any vector in R3 with a 0 in the last entry, right? Because if I want something of the form like xy0, this is equal to x1, 0, 0 plus y, 0, 1, 0. Okay? So these two vectors do span this column space, and we know they're linearly independent. And so that means that they do form a basis of the column space of the row-reduced echelon form, okay? And maybe I should notice also, as an artifact of row-reduced echelon form, that these are the pivot columns. Okay? So the pivot columns in row-reduced echelon form do form a basis of the column space of the row-reduced echelon form. Okay, in this case, the pivot columns, by the definition of row-reduced echelon form, they're always going to look like these kind of standard basis vectors. They're going to look like 1, 0, 0, and 0, 1, 0. And if there was another one, it would be 0, 0, 1, right? And so these things will span the column space, and they will be linearly independent. But that doesn't tell us, how to find the column space of A, right? So this just tells us something about the row-reduced echelon form of A. Okay. So we need to talk about this and say, like, so how does this tell us anything about A? How does this tell us something about A? Well, in general, if I have some matrix A just given by columns, let's call it V1 up through Vn, okay? Well, maybe I'll call it B, actually. If B is some matrix V1 through Vn, and let's say that the row-reduced echelon form of B is equal to just, I'll call them some new columns, V1 prime through Vn prime. So I have a matrix B, which has these vectors as columns, and I row-reduce it, and I now get these new vectors as columns. Okay. Well, then, if I have a solution, if I have a linear combination of the V1 through Vn's, a linear combination of the V1 through Vn, so C1 V1 plus up through Cn Vn, if this is equal to the 0 vector, this is true if and only if the same linear combination of these other vectors v1 prime through vn prime is equal to 0, is equal to the 0 vector. Oh, that c1 here should not be a vector, so it's just a scalar. And why? Well, it's because in both cases, the vector c1 up through cn is a solution to, bx equals 0, or row reduced echelon form of bx equals 0. Right? The point is, if I'm trying to solve bx equals 0, how do I do it with row reduction? I reduce it so you get the row reduced echelon form of b. And we know that if you're trying to solve bx equals 0, you row reduce it and get the row reduced echelon form of b, and the solutions don't change, right? That's the whole point of doing echelon form or row reduced echelon form, is that you get a simpler matrix, but the solutions are the same, right? You're doing this from day one. We're doing this to solve linear equations. So whether we look at solutions to bx equals 0 or solutions to row reduced echelon form of b times x equals 0, the solutions are going to be the same. And what that translates to in terms of linear combinations is that a particular linear combination of the columns of b is going to be 0 if and only if that same linear combination of the columns of row reduced echelon form of b is also going to be 0. So another way of phrasing this, so I'll say, in other words, linear dependence relations for columns of B correspond to those for columns of row reduced echelon form of B. Okay, so maybe I should draw a little line here, right? So we did something up here that told us how to find a basis for the column space of row reduced echelon form of A. We just used the pivot columns. So we want to go to A, and well, now we're seeing, okay, well, if you have some general matrix B, A is going to be the specific matrix, B is just a general matrix, then B and its row reduced echelon form are related in some way, okay? So on the next page, we're going to turn this into the actual way that you figure out how to write down, what the column space, a basis for the column space of A. Okay, so we're going to do this all on the next page. So by the way, we should just demonstrate this just with an example. I'm going to write this over here, maybe in purple. So A, I'm just going to rewrite the matrix that we had here. The matrix A was -3, 6, -1, 1, -1, 1, -2, 2, 3, -1, and 2, -4, 5, 8, and -4. And so, for instance, what do I mean by the linear dependence relations for the columns of a matrix correspond to the same ones as those for the row reduced echelon form? Well, let's look at this matrix A. What's a linear dependency here? Well, we know that if I take 2 of the first column plus 1 of the second column plus none of anything else, that's the same thing. That's going to give me 0, right? 2 of this plus 1 of this plus none of anything else gives me 0. Well, what we know is that the exact same relation has to hold for the row reduced echelon form. If I take 2 of the first column, 1 of the second column, and none of the other ones, that should give me the 0 vector. And clearly it does, right? 2 of this plus 1 of this is going to give me 0, and then everything else is 0. So just like 2 times the first column plus 1 times the second column here gives me the 0 vector, likewise 2 times the first column plus 1 times the second column here is also going to give me the 0 vector. Okay? So relations that hold with one of the matrices, either A or row-reduced echelon form of A, are also going to hold with the other one. Okay. So what does this tell us about trying to find a basis of the column space? Okay, well, we know that the pivot columns of row-reduced echelon form of A are linearly independent. Right? There is no linear combination of those pivot columns that gives you the zero vector. Right? Those pivot columns are exactly, what we had here. I'll draw them in green, right? The pivot columns were exactly this first column and this third column, right? And so they're linearly independent because they're just standard basis vectors. There's no possible linear dependencies among them. So I guess I should say from what we have down here, we know that linear dependence relations for A are the same as linear dependence relations for row-reduced echelon form of A. So that means if you have columns of row-reduced echelon form of A that are linearly independent, then for A itself, they also have to be linearly independent. So the corresponding columns of A are also linearly independent. Okay, so the fact that the pivot columns of the row-reduced echelon form of A are linearly independent, that implies that the corresponding columns, so in this case, the first and the third column of A, are also linearly independent, right? So if we check this -312 and -125, those are also linearly independent. Okay. So now I want to claim that they in fact span the column space of A. Okay. So what we also know, that the non-pivot, that every non-pivot column of row-reduced echelon form of A is a linear combination of the pivot columns. All right, so we know that every non-pivot column of the row-reduced echelon form of A is a linear combination of the pivot columns, right? Going back to this, we have our pivot columns 1, 0, 0, and 0, 1, 0. The non-pivot columns are all of these other vectors that have a 0 in the last position. But what we showed is that any vector with a 0 in the last position can be written as a linear combination of these two vectors. So every one of these columns is a linear combination of these two. But as holds for the row-reduced echelon form, the same thing has to hold for the non-row for the original matrix, right? So if this column right here, the fourth column, is -1 of the first column plus 2 of the second column, right? That's a 2. Then the same linear relation has to hold. Okay, for this fourth column here, it has to be -1 of the first column plus 2 of this second column. And it turns out that that's going to be right. Okay, you can verify that this fourth column of A is -1 times the first column plus 2 times the second column. So the upshot here is that the same must hold for every non-pivot column of, or maybe if every non-pivot column of A. Okay, so every non-pivot column of A is also a linear combination of the pivot columns. Okay. So we have that the columns of A corresponding to the pivot columns are linearly independent. And also anything that's not a pivot column lies in their span. So I can say, i.e., every column of A corresponding to a pivot column corresponding to a non-pivot column of the row-reduced echelon form of A is in the span of the columns of A corresponding to the pivot columns of row-reduced echelon form of A. Okay, right? Any column corresponding to a non-pivot column is a linear combination of these ones that correspond to the pivot columns, right? In this case, the pivot columns are 1 and 3, and we know that any one of the other ones, 2, 4, or 5, is going to be a linear combination of 1 and 3, because the same is true in row-reduced echelon form, so it's got to be true for the original matrix also. And what that means is that if we're going to take the span of all of the columns of A, well, we don't really need column 2, column 4, or column 5, right? Because these columns are already in the span of columns 1 and column 3, right? 2, we know, is in the span of 1 and 3. 4 is in the span of 1 and 3. And 5 is in the span of 1 and 3. Okay? So what that means is the column space is the span of all the columns, but really, you can take just the pivot columns. Okay? So what's the upshot? I'll write this in red because this is the big conclusion. So the upshot is that the column space of A is spanned by the columns corresponding. I'm saying corresponding to be careful, but I could really just say the pivot columns to the pivot columns of row-reduced echelon form of A. The column space of A is spanned by the columns. This is from also no. This is from also no above, right? This from this also no here. And then furthermore, these columns are linearly independent. Okay, this follows from no, right? So this follows from the first thing, or no, up here, right? And well, so what we have is these columns, they span the column space of A and they're linearly independent. And so that's going to mean that they're a basis. So we conclude that the columns of A corresponding to the pivot columns ones corresponding to the pivot columns of row-reduced echelon form of A, that these form a basis for the column space of A. Okay, so this is how we write down a basis of the column space of A. You row reduce the matrix, you find the pivot columns, and then you take the columns of the original matrix, not of the row reduced echelon form. You take the columns of the original matrix that correspond to the pivot columns. So for our example, if A is just the same matrix, I'm just going to write it down again, this matrix we've been using as a running example. So if A is, -3, 6, -1, 1, -1, 1, -2, 2, 3, -1, and 2, -4, 5, 8, -4, then a basis for the column space of A is, well, what do? You row reduce it to row reduced echelon form. You find the pivot columns. It's the first and the third. And so what you do is you just take the first and the third columns of A itself. So in this case, the basis for the column space of A is just given by -3, 1, 2, and -1, 2, 5. Okay, so this is a linearly independent set that spans column space of A. Okay, so just to recap, we have that if you want to find a basis for the null space of A, you just solve the equation AX equals 0, write it in parametric form, and the vectors that you get form the basis. If you want to find a basis of the column space of A, you row reduce and find the pivot columns, and then you just use the columns of A that correspond to those pivot columns. All right, so this is the algorithm that works for any matrix at all. Okay. So that's all I want to say about that. So we're almost done. I want to just say maybe 10 more minutes. I want to talk a little bit about chapter 2.9. So that was all 2.8. I just want to give a couple of definitions in 2.9, and we'll do the more involved computational stuff next time in person on the 19th. Okay, so all I want to do is just a couple of definitions, just because they're related to basis, it's worth doing them now. So definitions. The first one is if H is a subspace of Rn, its dimension, so the dimension of a subspace of Rn is the number of elements in a basis. And maybe I should say fact that every basis has the same number of elements. Right, so you're not going to have a subspace of Rn that has like one basis that has 2 elements and one basis that has 3 elements. So an example would be that Rn itself has dimension n. Right, because we know that a basis for Rn can be given by E1, E2, up through En. So there's n elements. So Rn has dimension n, which is, what you would think, right? I mean, R2 is a plane. It should have dimension 2. If we're going to define the word dimension to mean something, it had better tell us that the plane has dimension 2 and that, space has dimension 3, right? Otherwise, it's kind of a silly way to define the word dimension. But it turns out that this is the right definition of dimension. Okay, so if you have a subspace, what does its dimension mean? It means you count the number of elements in a basis. And that's what the dimension is. So the second definition, which is one, so if A is a matrix, then rank of A is equal to, so this is another definition, is equal to the dimension of the column space of A. So write dim for dimension, right? So this is a definition here, right? Right, so what does it mean to say the rank of a matrix? We mean that it's the dimension of the column space of A, meaning the number of basis the number of entries in elements in a basis of the column space of A. What did we see beforehand? We saw that in order to find the basis of a column space of A, you take the columns of A corresponding to the pivot columns of the row reduced echelon form. So this says that this is equivalent to defining the rank of A to be equal to the number of pivot columns of the echelon form of A, or the row reduced echelon form of A. Okay, so this concept, the rank, it's a number, and you can say either it's the dimension of the column space of A, or you can say it's equal to the number of pivot columns of A, or really more precisely stated, of the row reduced echelon form of A. Okay, so those are the two definitions, right? So we're defining the dimension and we're defining the rank. So we've seen that, right, so we know that the dimension of the column space of A is equal to the number of pivot columns. I'm just writing this again. Of row-reduced echelon form of A. What about the dimension of the null space of A? Well, this is equal to, well, how do we do the null space of A, right? We decided to solve AX equals 0 and write the answer in parametric form. But when we're solving, AX equals 0, matrix A, and we're writing the answer in this parametric form over here, well, the idea is we get a vector for each free variable, right? We got a vector for x2, x4, and x5. So in this case, the null space of A has dimension 3 because its basis, we have a basis with 3 different vectors, right? So we have x2, x4, and x5. We got these 3 different vectors, and so you get a 3-dimensional vector space. And how could we know that number 3? Well, 2, 4, and 5 correspond exactly to the non-pivot columns here. Okay. So what that tells us is that the dimension of the null space of A, this is good for a general matrix, is just the number of non-pivot columns of the row-reduced echelon form of A. And remember, this top one up here is also called the rank of A. This is not in the book, but sometimes you'll see this definition. I'll just write it in green. This is sometimes called the nullity of A. Okay, the dimension of the null space of A is sometimes called the nullity of A. So what we have is a theorem. This is what I'm going to finish with today. So a theorem, but the proof is immediate. So if A is an m by n matrix, then, well, the dimension of the column space of A plus the dimension of the null space of A, which is the same thing as saying the rank of A plus the nullity of A. Well, what is it? Well, one of them is the number of pivot columns of A, or row-reduced echelon form of A. The other one is the number of non-pivot columns of A, or the row-reduced echelon form of A. So when you add them together, you just get all the columns, right? You have the pivots and the non-pivots, so that's everything. So it's just equal to the number of columns of A. So number of columns of A, which we said A is an m by n matrix, so this is the same thing as n. So the dimension of the column space plus the dimension of the null space equals n. So in our example, our running example for today's lecture, A was a 3 by 5 matrix, and the rank of A was 2, right? We had 2 pivot columns here, the first and the third. And the dimension of the null space of A we saw was 3, right? The dimension of the null space of A was exactly this. It was 3. It was null space of A was span of these 3 things, and they were linearly independent. So another way of stating that is that the rank of A is equal to 2, and the nullity of A is equal to 3, and n was equal to 5, right? The number of columns is 5, rank of A was 2, nullity of A is 3, and 2 plus 3 equals 5, right? So it's an example of this theorem. Okay, so the very last thing I'm going to say, we're not even going to do a full page here, is just a particular case. So in particular, if A is n by n, so if it's a square matrix, then A being invertible is equivalent to, well, the rank of A. Well, if A is invertible, what do we know about the rank of A? Well, if you go back to the invertible matrix theorem, we know that A being invertible means, among other things, that its row-reduced echelon form is the identity, right? If A is invertible, we can row reduce it to the identity. And that means that every column is a pivot column. So that means that the rank of A has to be n, right? So if A being invertible is equivalent to rank of A being equal to n, right? A is invertible if and only if the rank of A is equal to n. And I'll say that it's also invertible, also equivalent to the nullity of A, the number of non-pivot columns. Well, if you have an invertible matrix, we're saying we've got the pivot columns. Every column is a pivot column, right? So we have n pivot columns. We don't have any non-pivot columns. So it's also equivalent to the nullity of A being equal to 0. Okay, so being invertible is the same as the rank of A being n, and it's also equivalent to the nullity of A just being 0. Okay, so next time, okay, so that's it for now. And then next time, we're gonna talk a little bit more about bases. Bases, that's the plural of basis, is bases. So we'll talk a little bit more about bases and how to compute with them. Okay, so thanks for listening. Enjoy the rest of your day, and I will see you in class on Wednesday.